happy to have Silas all the way from the other coast. Tell us about high-dimensional Goldreich-Levin.
All right, thanks for having me. My name is Silas Richelson, and I'm going to tell you about a high-dimensional Goldreich-Levin theorem. It's joint work with Parker Newton and Chase Wilson. So Goldreich-Levin theorem is absolute cornerstone in theoretical computer science. Fundamental result in cryptography and Boolean learning theory, coding theory, and maybe an overstatement to say that it's everyone's favorite theorem, but it's certainly it's in the Hall of Fame for sure. Informally, what it says is it's an algorithmic theorem, an algorithmic result. It says that if you have oracle access to some function, where the function has good linear agreement, then you can efficiently recover somehow that linear agreement. You can efficiently recover the linear map which agrees with your function. And I'm going to explain, I guess, the model. What we mean, maybe this is like review, but what we mean when we say we have oracle access is we're sort of just given input-output access to the function. We can feed it inputs, we can get outputs, but we don't have access to any code. We're not attempting to learn anything about the function other than what we can learn by just viewing what it does on certain inputs that we feed it. So that's kind of the model, pretty standard model. What I mean when I say it has good linear agreement is there exists some, let's say, vector u, string u, such that with good probability, f of x is going to equal x dot product with u. And this is, I'm using like terminology from linear algebra. And you can generalize this to sort of work over vector spaces over finite fields. But I'm going to stick with kind of binary 0-1 strings for this talk, just for simplicity. So specifically, this dot product is going to be like u1 times x1 plus u2 times x2 and so on. And yeah, so again, the Goldreich-Levin theorem says that if you have oracle access to some function and that function has some linear agreement, you can recover the linear map u that it agrees with. And again, we're only using the input-output access to the function. We're not trying to like look at the code of the function and try to like decipher u in that way. That's not what we're doing. And so, okay, I just kind of replaced good linear agreement, the informal thing, with like the probability that f of x equals u times x is large. And I guess sort of to start, I wanted to show like how this theorem works and what it says in like the very simple and special case when like the probability of agreement is just 1. It's perfect agreement with a linear function. In this case, pretty clearly, you can just feed it sort of, the string 1, 0, 0, and you're going to get the first bit of u, 0, 1, 0, 0, 0, you get the second bit of u, and so on, and you can recover the entire string u using the perfect agreement. As soon as the agreement is a little bit less than 1, you kind of like that's not going to work because the function's now allowed to make some errors, and so it might make an error on e1, e2, and like you can't rely on any specific string giving you the correct output. But okay, you can sort of like use some probability. You choose a random basis for the vector space 0 to the m, and you feed all the basis vectors to the function, and you look at the output. And we'll use sort of the fact that like if you choose a random basis, then the marginal on each basis vector is just completely uniform. So that means that like each of these is going to be correct with probability 1 minus delta. And so by union bound, if delta is small enough, we can recover the full u this way. And I'm not going to continue. I'm not going to like prove the full Goldreich-Levin theorem this way, but hopefully you can see that like as this probability, this sort of, is this a laser? How does it work? Sorry.
It's right above the arrow keys.
Cool. Okay. Can you see that, or is that sort of silly? Okay. So as this probability gets further away from 1, you have to work harder to recover u. And the Goldreich-Levin theorem says, this is sort of a more formal statement. It says that if you're given oracle access to a function, such that there's some u that has agreement that's pretty far away from 1, pretty small, 1/2 plus delta for any delta, then you can efficiently recover u. And one of the striking things to me about this theorem is this like number 1/2 plus delta. It's sort of optimal in the sense that like you have no hope of recovering u if the agreement is 1/2, because a random function is going to have agreement 1/2, and there's no structure there. You can't recover anything. And so what Goldreich-Levin is saying is that if you have any agreement that's better than sort of nothing, you can efficiently recover u. And okay, to be formal, like once you get this far away from, once the probability gets this far away from 1, there might be more than one u that has this property. And Goldreich-Levin says no problem, you can recover the full list of u's that have good agreement with your function in time that's like, basically efficiently.
So in particular, the list will be small.
Correct. The list will be small. You can show that, and then you can recover the entire list in time. The list size, I think, is like delta square, delta to the -2. You can show, and okay. I mean, this came out in '89. This was a striking result. It had a lot of applications. I'm going to say a couple. In cryptography, if you just kind of recast the statement of Goldreich-Levin into like cryptographic terms, what it says is that if you have some type of like cryptographic secrecy, then the bit u times x is going to be pseudo-random. And this is like massively useful to cryptography. Basically what it says is that one-wayness implies pseudo-randomness. And the reason it's so useful is that pseudo-randomness is often kind of what you need to get cryptographic applications. But one-wayness is kind of what you run into when you try to write algorithms for hard problems. And so Goldreich-Levin gives you kind of a smooth way to convert sort of a difficult algorithmic problem into something that you can use to build crypto. And, you know, this led to just a ton of different results of the type of like one-way functions imply like, you know, whatever primitive you want, not literally, but like many different primitives of cryptography are known to come from one-way functions. Lots of different results here. And it's still common today. Like this comes up all the time in modern crypto. You're trying to build these, you know, big, complicated crypto schemes, and you run into some sort of situation where you have some hardness, but you need pseudo-randomness, no problem. You use Goldreich-Levin and you get it. This is like a completely standard tool in the tool shed or whatever of the modern crypto. Okay, in Boolean function analysis, if you recast the statement of Goldreich-Levin in terms of, you know, the language of Boolean function analysis, it says that given oracle access to some function, you can recover the heavy forward coefficients. And this is extremely useful in lots of different contexts in Boolean function analysis. In coding theory, this is what I want to talk about a little bit more about. The Goldreich-Levin theorem gives you a decoding algorithm for the Hadamard code. And so just to explain a little bit, you know, the model in coding theory is you have sort of, you know, somebody that's the sender trying to send a message to a receiver. And, you know, maybe some string u you're trying to send, and the channel has this like noise on it where with the property that like every string that you try to pass over the channel, some of the bits are going to get flipped. So here, if you know, this is the string that Alice tried to pass, and then these red bits are the ones, are the errors that were kind of imposed by the channel being noisy. And so what you're trying to do is to use this noisy channel to perfectly send your message without any errors at all. So what Alice is going to do is she's going to take her u, she's going to encode it into some longer string e of u, and then she's going to send that over the channel. Bob's going to recover some other sort of corrupted version of this code word, sort of y that's like, you know, most of the bits of y are equal to the correct thing, but, you know, he's not sure which one, and he's going to try to decode to recover u. Okay, totally standard coding theory setup. The Hadamard code is a particular code where you encode a string u into a string of size 2 to the m. So this is sort of like a bit string where the bits are indexed by strings in 0 to the m, where sort of the bit corresponding to x is going to be u dot x. Totally standard code. Oh, one thing I want to say sort of in this picture already, you can kind of see here like a tension between the two most important parameters in coding theory. One is the rate, which is basically like how much you have to explode the message. How much longer is the code word than the message? Versus the essentially the chaos of the channel. How likely is it that a bit sent over the channel is going to get flipped? And, you know, if you think for a little bit, it's pretty clear that the higher the chaos of the channel, the longer you need to make your message. And the Hadamard code represents, so there's basically a trade-off. And the Hadamard code is like an extreme code. It's an extremal point in sort of the rate distance trade-off. And basically the rate is really bad, like you're blowing up the code word quite a bit, but you're gonna get excellent distance. And okay, yeah, I'm just saying, think of the code word of u as like a function that sends x to the x in product u. Okay. Yeah, and so, okay, this is the Hadamard code with the same model. So Alice wants to send u, she encodes u by sending the entire truth table of this function eu, where eu is the function. Bob's going to recover some truth table of some corrupted function that sort of like has good agreement with eu, but it's not completely equal to. And then if you recast the Goldreich-Levin theorem in sort of this setup, it says that, okay, Bob has an algorithm that he can invoke on this sort of received corrupted truth table to recover u. Okay.
Looking at most.
Correct. And yeah, that's a good point. So it's so I say here, this was like the first local list decoding, and local means basically that the runtime of this decoding procedure is not linear in the size of the code. The size of the code is huge. It's linear, or not linear, it's efficient in the size of the code word that we're looking for, which is much, much smaller than the whole truth table. Okay, and that sort of, in coding theory, that's called being like a local list decoding algorithm, if you know what that is. Local meaning you're not reading the entire code word, you're just sort of running efficiently and looking for what you want. And this was the first local list decoding algorithm. Tons of them have followed. It's completely standard now in coding theory, and there are many more works just besides these. These are just some. So this was like a very groundbreaking work. Okay, this is sort of something I wanted to say because it kind of, this is a little bit of backstory. It's like how we got to how we sort of stumbled upon this problem to solve. And you could sort of maybe say that the Goldreich-Levin hypothesis might be a little artificial. Like, in what sort of setting are you going to have this guarantee that F is like has a linear agreement, except if you're sort of building that in as a hypothesis? Maybe you could maybe argue that. But there are other works that kind of start at a different point. They're still working with the Hadamard code, but sort of there's a very famous and important result of BLR and a new analysis of Bellari et al., where basically they're looking at a different aspect of the code. They're trying to sort of test whether a function is linear or close to being a linear function using a very small number of queries. So what you do is you choose x, you choose y randomly, and then you ask, does f of x plus y equal f of x plus f of y? And clearly, if it is a linear function, this will pass with probability 1. And what BLR show is that if the probability of passing the test is like any better than just random, any better than 1/2, then it has agreement 1/2 plus delta. And this sort of is kind of the starting point of Goldreich-Levin. And so what this means is that you can kind of stumble into the hypothesis of Goldreich-Levin just by looking at very efficient tests for your function. And that's a useful thing. That's how we sort of like stumbled onto this question. We were trying to prove some like lower bound in cryptography, and we realized that this function that we had some sort of linear structure, it passed some test, and then we're like, great, it was a high dimensional function. We're like, great, let's use a high dimensional version of Goldreich-Levin. We're done. Then we like looked through the research. We're like, oh, I guess no one's proved it. And then sort of we stopped and tried to prove it. That was kind of how we got there. But basically, this combination of like sort of a test passing, giving you some linear agreement, and then you can get an algorithm from some type of Goldreich-Levin. It's a really useful combo, and I think it's. I'm not aware of like specific places where this applies, but I've used it more than once, and I think it sort of shows up. It's kind of a common little trick. Any questions that make sense? Okay. Yeah, so this is, if you want to cast this sort of thing in terms of coding theory language, what this is saying is basically the Hadamard code is locally testable. And so Goldreich-Levin comes downstream of a local testable result to show that you can actually algorithmically recover the structure that's making you pass this test. Okay. Yeah, and this is kind of the combination theorem of BLR plus Goldreich-Levin. If a function passes this 3-query BLR test, then you can equivalently recover, you can efficiently recover the linear function, which explains all the test passing success. Okay, so Goldreich-Levin has been generalized lots of different ways over the years. You can sort of generalize it immediately to a large modulus. The same proof just works. You can generalize it to group homomorphisms instead of sort of like functions from the specific group ZQ to the M down to ZQ. You can sort of ask, okay, if you have a general group homomorphism that sort of passes the if you have a function between groups that has some agreement with a homomorphism, can you recover the homomorphism? This was asked and answered in some works. You can extend sort of the type of agreement that you're looking for. So there's this work of Tolsiani and Wolf, where they assume that you have some function that has good quadratic agreement, and they can like sort of efficiently recover the function with that agreement in that setting too.
Zmq had something earlier.
I thought that Zmq had the work of his that I'm aware of is a testing result, and it's but he does have a quadratic test in that paper. Yeah, that's right. Okay, and in this work, we're going to sort of generalize this Goldreich-Levin theorem to a different place. We're going to look at the case when the function has high dimensional output. So in particular, we're looking at a function that takes m bits of input and has n bits of output instead of just 1 bit of output. And we're going to prove Goldreich-Levin type theorems for these functions.
So do you know also something about testing?
Right, I'll say this. So testing in these high dimensional functions is actually a very hard problem. It's connected to additive combinatorics. I'll say I have a couple slides on that in a bit. But no, our result does not give anything new for the testing, but I'll talk about it. Okay, so there's a little bit of work you have to do to properly generalize this question. So the setup again is you have some function, m bits of input, n bits of output, you have some matrix, and you have some agreement, sort of probability over random input that f of x equals a times x is epsilon, for some epsilon. And the question is, can we efficiently recover a? And the answer, actually, it's not hard to answer this question. This is kind of the wrong question. It depends on epsilon. Certainly, if epsilon equals 2 to the negative n, then there's no hope. In this case, f is like a random function, has agreement to the negative n with some matrix, with every matrix. And so you're not going to be able to recover anything from such a function. If epsilon is bigger than 1/2 plus delta, then you're kind of in the setting where the old Goldreich-Levin theorem works. And so you can recover it in this just using prior work. And I mean, the original Goldreich-Levin works to basically just recover the matrix. Sort of more interestingly, if as soon as epsilon is less than 1/2, the answer is no, you can't actually recover a. So to see this, you can kind of consider this counterexample function or just example function. And this function sort of turns out to be, I mean, in my experience working with this problem, it's not like a sort of formal statement, but this turns out to be, I think, like the hardest counterexample to kind of get around. A lot of the analyses that you hope works kind of fail because of this type of function. So, okay, what's this function? It's basically just, it outputs a times x, except for the first bit, which is random. Okay, so it flips a random point for the first bit, and then the rest of the output is just agreeing with a. Sorry, I'm not watching Zoom. Are there going to be like chat questions and stuff?
Yeah, you will hear.
I will hear. Okay.
You will hear them. They shout and you will hear.
Okay. So yeah. Okay. Here's a function. Clearly, yeah, f of x equals a of x except the first bit, which is random. Clearly, the probability that agrees with f is 1/2. It's just whether you got the first bit correct or not. However, this is going to hold, namely probability that f of x equals a prime of x is going to hold for any a prime that has that agrees with a except for the first row. And that makes sense. There's no information in f about the first row of a. So any matrix that agrees except for the first row is going to work just as well as a. And that's an exponential size family of matrices. There are 2 to the m matrices that agree with a outside the first row. And they're all sort of equivalent as far as algorithmic, as far as the algorithm is concerned. Any algorithm that recovers a should recover everything in this list, but it's an exponential size list. So you're not gonna be able to efficiently recover a. Okay, so that's sort of no bueno, right? You have sort of this, it kind of seems like this sharp threshold that we had for Goldreich-Levin sort of extends up to the high dimensional case too. Yeah.
Just checking my understanding. So another counterexample would be like if f only really output 1 bit and the rest was just zeros.
Yeah, that would be like the example that it's the previous example, but where a is the zero matrix.
Right.
So yeah. So yeah, okay, again, it seems kind of like the same Goldreich-Levin bottleneck of okay, if you're at or below 1/2, it's hopeless. And if you're above 1/2, even a little bit, then Goldreich-Levin says you can recover a. It seems as though that characterization extends up to here. Yeah, so that's not so good. However, it's very unsatisfying to sort of stop there. The reason is, in Goldreich-Levin, you had a reason why 1/2 was impossible. 1/2 was like the randomness threshold, where there's clearly no structure. Here, the randomness threshold in sort of to the negative n, where you have no hope because of a random function, and 1/2 plus delta, where sort of Goldreich-Levin works. And so it's not just because you can't recover a, it's not clear that you can't recover sort of the structural information about the function that is explaining the linear agreement. And so, okay, maybe we just need to move the goalpost and change what we're trying to do. And yeah, this is what I just said, sort of huge gap between this 2 to the negative n, where there's no hope clearly, and 1/2 plus delta, where the Goldreich-Levin theorem works. So the question is kind of what's possible in between here. Okay, so maybe we can't recover a, but what can we do? And before we can sort of to motivate our answer, let's look again at this counterexample. Somehow, the reason that this failed was that there are an exponential number of matrices that kind of all could be subbed in for a, and so for that reason you can't hope to recover a specifically. And the key point is that the whole exponential size of the whole exponential family of matrices, they all agree with that for the same reason. So it shouldn't be our goal to recover everything in the family. It's repetitive. It's all going to be the same. Like you're just going to recover A rows 2 through n, and then some meaningless first row. So we shouldn't attempt to recover like the matrix A. Really what we want is kind of the explanation of why the linear, basically we want rows 2 through n of A, not, we don't care about the first row. Okay, so that question that we want to answer, what's possible between 2 to the negative n and 1/2? Okay, well, we can't recover A, but can we recover some A prime that's sort of like morally just as good as A? Namely, in this case, I want rows 2 through n of A. And the answer is yeah, we can do this. So that's sort of what we wind up doing. So this is the main theorem. I'll read it. So there's an efficient algorithm which gets oracle access to a function from m bits of input and n bits of output. And it's going to output a short list of matrices, L, such that 2 things hold. First of all, everything in L has good agreement with F. And second of all, every matrix that has good agreement with F has good agreement with something in the list. Okay, so in terms of like sort of matrices explaining quote unquote other matrices, this is what I mean. Basically, like there's good agreement between A and A prime. And so intuitively what this is saying is we can recover like a succinct short list L that explains all of the linear agreement, even if we can't recover explicitly all the different matrices A.
And this epsilon square means it's unique also, right?
In what sense do you mean it's unique? Like
There's a unique A in L such that.
Right, yeah, because you're gonna have distance.
Different ways.
Exactly, right, because if it was, then you basically are being inefficient. So we're kind of like,
You could probably also just prune away.
yeah, exactly, that's how we do it basically, yeah. You sort of find something that has good agreement and you prune, you change the function to remove all the points of agreement and kind of iterate. So a couple of things about this theorem. This epsilon is, you know, it's exponent. It's going to be optimal up to that constant in the exponent. You could possibly work harder and get some type of like additive error where like it works for epsilon that's like 2 to the negative n plus some additive delta and try to work there. So that's sort of one way to possibly improve it. I think a more sort of in my opinion, kind of the more important way to improve it is what we mean by efficient. So it's our runtime is going to be exponential in log of 1/epsilon, which is not ideal. Ideally, we would have constants here. And so this sort of suggests that like our algorithm maybe can be improved to not have this runtime. I will say that sort of we prove a theorem that holds over like general, you know, finite fields or ZQ or whatever. And the exponent here is log base Q of 1/epsilon. And so that's kind of going to get less and less offensive as Q gets bigger. And so, you know, but the sort of special case of Q equals 2 is like the one where our algorithm runs the slowest. And yeah, getting an improvement in that case is, I think, a good open question. And so yeah, that's the theorem. Again, this is kind of the intuition. Recall that this sort of, the set of matrices which have good agreement, it could be exponentially large. So what we're saying is we're going to output a small subset which explains the full exponentially sized set. Yes.
If you drop the second requirement, is the problem much easier?
If you drop this second requirement,
Yes.
yeah, you can. I see. I'm not sure that it's easier to solve. I think sort of once you find a matrix A that has good agreement, it's sort of like a pretty basic standard argument to then convert that into. You know, you can do the pruning operation where you like prune out all of the inputs of the function that agree with that matrix you just found, and then you can solve it again. And kind of recursively, you'll recover this short list. So I think like what we're actually going to prove here is kind of, we're just going to show how to find some matrix A. And I'm not sure that the theorem would be any easier to prove if you remove it, although it's somehow like less fulfilling because you want to basically, like this is very sort of in the spirit of list decoding, where you want to like explain all of the structure with a short list.
That's true, but short, I guess, depends on epsilon. So if epsilon's very, very small, then this actually has to be quite big.
Yeah, of course, but there's no way around that because like you could, F could just be alternating between epsilon, 1/epsilon different matrices. And so you'll never be able to shorten the list beyond.
You understand what it means alternating? One can pick, you know, 100 matrices A and use them to define a function where on some random set, it's the first A1 of X, on another random set, you have partitioned the space into 100 random sets, and in each one answer consistently with one matrix. There's no way to have a list shorter than 1/epsilon.
Yeah, but in that case, like, wouldn't it be much more efficient to abandon the goal of getting all of them?
Yeah, so one good question, I guess, is whether you can solve just the first condition in polynomial time in 1/epsilon.
In polynomial time
Without having, it's a good question. Whether you need the exponential
right.
Dependence on log 1/epsilon if you only wanted to.
Yeah, it's a good question. And actually, like, the reason we have this dependence is because it takes us that much time to recover a single one. Sort of converting that into the full list doesn't.
Oh, you don't know.
Correct, I don't know, yeah.
I have a stupid question. Like in 2, the probability that A prime X is equal to AX, I mean, so what this really means is that like you have like a really small kernel of the difference. I mean,
Yeah, they differ by a low rank matrix.
I see. So it's not like Hamming distance or something.
No, they could disagree on every single input. It's just like, I mean, you could imagine like you add the constant matrix 1 to everything. They'll differ by low rank, but they won't. I mean, they'll agree on a lot of their inputs, even though sort of Hamming distance they disagree everywhere.
Oh, I see. But this is like the right notion, right? Not Hamming distance, because
Hamming distance between the matrices?
yes.
There should be no reason that there be.
Right, because
You want the function to have a close Hamming distance or correlation.
yeah. Because if f of x is equal to a of x and a is equal to a prime, then f of x will also be equal to a prime. So this is like the
Maybe, although these are all small probabilities, so it's possible that they just are not. Like, just because f of x equals a of x on a small portion of the inputs and a of x equals a prime of x on another small portion of the inputs, there could be no overlap. But so specifically what we're saying is that any matrix A prime, possibly not in the list, that has good agreement with F, it sort of has to have some it has to have some matrix in the list that it agrees with. And in practice, it will sort of correspond to the points where A prime equals F.
But on the other hand, if the matrices are close in Hamming distance, it says nothing about the function.
right.
You can have, if you add the I to your matrix, let's say square, then you will have opposite answers, complementary answers to every input, right? So, and that's not what we want.
Any more questions? Okay, so just like sort of the original Goldreich-Levin gave an decoding algorithm for the original Hadamard code, our result is going to give a decoding algorithm for the high dimensional Hadamard code. What I mean by that is the code, which the input, sort of the code word is the message is a matrix A, and the code word is going to be like the truth table of this like matrix multiplication or vector matrix multiplication. Namely, it's the truth table of the function that sends x to the vector ax. And yeah, our result sort of in the language of coding theory, I'm not going to sort of explain what this is from scratch, but in the language of coding theory, our result gives what's called an approximate list decoding algorithm for the high dimensional Hadamard code. And if you know what a list decoding algorithm is, an approximate list decoding algorithm is like a generalization which extends to the setting where the list might be exponentially large. So, which is basically exactly the setting we're in.
So this definition existed before you?
Definitely, yeah. This is like a very well studied thing. It existed all the way back to the early 2000s implicitly in a lot of works that sort of used it to get some hardness amplification. And then it's become, it's made explicit at least in like 2017, I think, possibly before. And it turns out to be kind of the right gadget to analyze certain types of like code composition. So it's very useful and it is well studied. And it's approximate list decoding. It's the same as list decoding, but you try to basically increase the distance even beyond where you have this combinatorial bound on the list size, the place where the list size might be exponential, and you try to decode there.
So what defines it first?
The first time I was aware of it was this work by Amnon Tashma and Prahlad Harsha and some other people in, I think, 2016 or something. They have this paper called List Decoding from Double Samplers, I think. But it might be before. I mean, it was one of your papers in like 2009 where you used it to get, or maybe Luca Trevisan used it to get some hardness amplification theorems.
Okay, good. So
Yeah,
it was around.
It definitely was being used, and I don't know that it was like an explicit definition until more recently, but it was definitely like in.
So is it used for like miracles?
I think Luca Trevisan was maybe the first to show that like he had this connection right between like list decodable codes and like extractors or something.
Yeah.
And he was the one to show that sort of this was the type of decoding that you needed to get a good extractor. I apologize if that's wrong. I think that's sort of more morally kind of what he showed.
Probably like in the direct product codes.
Yeah.
So like you can agree with the function, but then like you can change the function just a little bit and you still agree with it. So
Yeah, but that's very different. Here you are in a regime with.
yeah, but like that's, I think that's like where this idea of approximate list decoding, right? That's like where people looked at it, where you can't.
The limit is very small. It's small, right? It's tiny. Well, it's necessary. I understand. No, I mean, given. I was wondering where it started. Anyway, so it's pretty recent.
Yeah.
If you think about it, it's the middle of the last decade. I mean, list decoding has existed since the 90s.
Yeah, I think that also approximate list decoding is kind of the gadget that you need to compose codes and get a good list decodable code in the same way that you compose normal error correcting codes, you get a better error correcting code.
Also, you usually work when the list size is small.
Yeah.
I think that all the PCP results, I think you work with when the list size is small. I just don't remember seeing this, but anyway.
Okay. Okay, and this is sort of back to your question. I think it was your question about local testing for the high dimensional Hadamard. It's actually an extremely well-studied problem. This is Znx's work, where, well, okay, you can try to prove like a high dimensional version of this BLR theorem where, you have some function with n bits of input, n bits of output, and you have some test passing probability where like if you choose a random x and y, chance that f of x plus y equals f of x plus f of y is at least epsilon. For some epsilon that's like small but bigger than 2 to the negative n. And there, a high dimensional version of BLR would say that, in this sort of like, given that f has this test passing probability, there's some matrix A such that like the chance that f of x equals a of x is at least epsilon prime. For some epsilon prime that hopefully depends on the other stuff. And there are theorems of this type. Znxmq proved one in 2007, which got an exponential bound on epsilon prime in terms of like 2 to the negative m and polynomial epsilon. And this was an amazing paper. He connected it to additive combinatorics and used sort of big heavy machinery from additive combinatorics. And since then, improvements to this theorem have come via improvements to the additive combinatorics that sort of were connected by Znxmq. So in particular, there's this result of Sanders in 2012, which he proved sort of a quasi-polynomial version of the polynomial Freeman-Ruja conjecture. It's a big conjecture in additive combinatorics. And using sort of his work plus Znxmq's connection, you can get epsilon prime to be quasi-polynomial in epsilon. And the open polynomial Freeman-Ruja conjecture says that epsilon prime depends only just polynomially on epsilon. And this is open, connected to a very very difficult, presumably difficult question in additive combinatorics. Yeah.
It's equivalent, right? I mean, if you compare this, it implies the PFR.
Correct. It's equivalent to some version. So the statement here is going to be equivalent to the PFR in like the group Z2 to the M. But yeah, you can state sort of a general group version of this, and it is known to be equivalent. Yeah, it's a good point. Okay, and our results in the same way that original Goldreich-Levin combines with BLR to get like an algorithmic version where you have sort of some function which has some test passing probability. You can kind of use BLR to say that there exists some linear agreement, and then you can use Goldreich-Levin to say you can recover efficiently that linear agreement. You have the same type of combination here. Oh, and I had a slide that I took out, but basically this is how we kind of bumped into this problem. We sort of had this, we were trying to prove something in just a lower bound crypto having nothing to do with anything. And we realized that because of sort of the setup of the problem, the function that we had to pass some type of linearity test. Not exactly this, but something that was kind of similar to this. Actually, it was the same test, but it had like high arity. So it was like instead of x and y, you choose x1, x2, x3, all the way through xd, and you check that like the long linear combination of the functions equals like f of the linear combination of the inputs. That test turns out to be much easier to analyze. You don't need to go through the additive combinatorics. Like you don't need to jump through these hoops. You can just use the original like Fourier analysis, BLR test analysis to get it. And so you say in that case that, okay, if you have some function that passes some version of this test, it like via, you can get that there's some linear agreement. And then we were hoping to just like invoke some high dimensional Goldreich-Levin, and it turned out it hadn't really been done yet. So that was kind of how we arrived at this. Anyway, for the rest of the talk, I want to talk about the algorithm and analysis. If that's okay. Any questions before we do? Okay, so again, we're sort of this algorithm designer. We have Oracle access to the function. We're feeding it inputs, we get outputs. And we're trying to, and we know that the function, we're assuming the function has good agreement with some linear map A. And our goal is to recover some matrix A prime that's like morally just as good as A. Okay, now we're gonna not really worry about this goal. We're gonna try to answer like a simpler question. If we feed it x and we get back f of x, how do we know if f of x equals a of x or not? Okay, this is kind of the crux of the question. If we can distinguish, if we can like tell whether we're getting a correct answer or not, we can, we can recover some a prime pretty easily. We just like choose a basis such that we're getting correct answers on all the basis, all the basis vectors, and then we just sort of put them together to recover a. Okay, so the key question is this one. Given like an input, like we send an input, we get an output, is it correct or not? How do we answer this question? At the starting point, all we know is this, that f of x equals a of x with some probability, but we have nothing better to say. So we get some, output, and then we're sort of left shaking our head. Is it good? Is it not? I don't know. Okay, so as a starting point to try to answer this question, we have a one-dimensional Goldreich-Levin theorem. Let's try to make use of it. It's kind of a natural starting point. So, we can ask the question, can we recover like the first row of A? Is that possible? And perhaps using the one-dimensional Goldreich-Levin theorem. And so what that would look like if it worked is we would say, okay, if this f1 is like the first coordinate function of f, and this a1 is like the first row of A, if f of x equals a1 times x with probability that's better than 1/2, then by just using the one-dimensional Goldreich-Levin, we'd be able to recover a1 with some probability. So this is sort of what using that would look like. Obviously, like we don't have this guarantee, right? This guarantee here, the like probability that the first row agrees with probability 1/2 plus delta, does not follow from this. It's pretty easy to sort of set up some functions where the first row agrees with probability epsilon.
But it's only for some or
Right.
even many rows.
Exactly. So, however, the first row might sort of not work, but we can recover some linear combination of the rows using the one-dimensional Goldreich-Levin. And so the key computation that sort of makes sure that this works is, I suppose it's like totally standard, but I'll do it anyway. We want to look at, so if z is like a row vector, an n or an n-dimensional vector, you can ask the question, what's the probability that z interproduct with f of x equals z interproduct ax? Okay, and in particular, let's look at the expectation of this over like a randomly chosen z. Okay, and you just do a calculation. This is just going to be, the probabilities kind of factor out this way, and you get basically 1/2 plus epsilon over 2, where epsilon is the probability of agreement. Okay, the way that, you can just do the calculation, or you can kind of understand that if f of x equals a of x, then this holds for every single z. And if f of x does not equal a of x, then it holds for half of the z's. And that's going to give you this. And so on average, we are in the setting where you're like 1/2 plus, delta. Okay, so we are in the Goldreich-Levin linear agreement regime on average. Okay, so this suggests a procedure. Let's choose a random z, and let's run one-dimensional Goldreich-Levin on the function f sub z. Okay, and sort of, hopefully we're gonna recover something that we want. So let's analyze. So we just showed that the expectation over Z of this probability is 1/2 plus epsilon. Okay, you can show that sort of with probably epsilon over 4 over Z, you're gonna have the probability is 1/2 plus epsilon over 4, pretty standard. And then if you have this agreement guarantee, then when you run the Goldreich-Levin theorem here, you're going to recover A transpose times Z. We're using the fact that Z times A of X is equal to A transpose Z times X. This is just linear algebra. And so to summarize, this procedure is going to recover one row, one sort of, it's morally equivalent to one row, but it's a linear combination of the rows of A with probably, epsilon cubed, roughly. Okay, and then if we sort of step back to our question of trying to understand whether f of x equals a of x, well, one thing we can do, we have this new ability to recover a linear combination of the rows. Okay, you could try to just apply it n times and hope that you get lucky. That's not going to work for an algorithm because it's going to decay exponentially. No good for us. But you can sort of do a little better. So that's not going to work. But you can do a little better. Basically, what you can do is you can run the procedure one time. You get one linear combination of the rows. And then you kind of you don't know that you got the right that you got the correct thing. You only have like a good probability of getting it. But you can say sort of assuming that I got it correct, let's double down on the linear combination of the rows and let's make this question now easier. And the key point is that if you feed x and you get back f of x and you're wondering whether f of x equals a of x, well, now you have a hint as to whether or not it equals a of x or not. You can check whether that one linear combination that you extracted is going to be satisfied. Okay, and so the probability that f of x equals a of x, given that the linear combination that you extracted holds, is going to be this conditional probability that f of x equals a of x, given that z times f of x equals z times a of x. And this is going to simplify to epsilon, the original probability, divided by the probability that this linear combination holds. And you're going to have made progress when this linear combination holds with probability bounded away from 1. Okay, so that's pretty confusing, but we can sort of, I'll get to the picture, which will kind of hopefully make it clear. Let me,
So now you're trying to sample x's, given that they satisfy the conditions that you would.
Yeah, basically what I'm doing is I'm choosing a random x, feeding it to f, and I'm receiving f of x, and I'm like, is that actually equal to a of x or not? And the answer is, well, I don't know, but it's certainly not equal to a of x if z times f of x does not equal z times a of x. So let's just throw those x's away, and let's only look at the ones where equality holds, and hopefully, the probability that this holds, given that this holds, is going to be just better than epsilon. Okay, and this is just kind of a type of greedy algorithm where, okay, you set the, S is kind of the, you set S, you initialize S to be the entire domain, and you do this main loop t times, where t is some number we'll pick later. You basically run the one-dimensional Goldreich-Levin procedure. You recover one linear combination of the rows of A. You update the set S to basically remove all of the points where the linear combination that you recovered does not hold.
Does not, it says.
Yeah, you keep the ones where it does hold. You remove the ones where, yeah. And then at the end, you output the set S. And as far as answering this question, I wonder if f of x equals a of x. Let's use membership in S, this set that we computed, as kind of like a proxy for whether you have f of x equals a of x. And so, when we're sort of, as the algorithm designer, feeding an x, getting back f of x, we're just going to say f of x equals a of x if x is in the set S. Okay, and so let's look visually at what this is doing. This will make it easier to understand. So this picture, S is this yellow set. It's initialized to be the entire domain. This blue set is the set that we're looking for. It's basically the set of x's such that f of x equals a of x. And it's a
We don't know A.
Correct, we don't know A. So we're hunting for.
Well defined.
Oh, let's assume that. Sorry, you mean that there might be more than one A, or?
Okay, you assume there is some A.
Correct.
I don't know.
Assume that there's some A, and so you have some set like this, and let's try to find the set. We don't know where this is, but we know it's somewhere. And so basically what this is going to look like is you run the greedy algorithm one time, you sort of S starts as the entire space. Now you recover one linear combination and you remove all the points that don't satisfy that linear combination. So now S is a little smaller. You do it again, you make S a little smaller. And you hope that by repeating this, you're going to get S to be equal to or very slightly bigger than the set you're looking for. Okay, and if
foundation on the fact that all the Z's you picked up in this process were good.
Correct.
And you lose the factor epsilon in that.
Correct. So basically, yeah, every time you do a step, you have like a small probability of being successful. So you want to minimize the number of steps you're taking for that reason, but you want to maximize like the chance that you get sort of the set to be equal to or marginally bigger than the blue set you're looking for. And okay, so what we hope to achieve by the end of this is that the chance that you're in the blue set conditioned on you being in the yellow set is like pretty close to 1. If you can get this, then you can kind of like recover A using. Okay, so here's the picture of the algorithm again. Like we initialized this S to be the entire domain. This blue is the set that we're looking for. It's the set of X's such that f of X equals A of X. And each time we run this procedure where we find one combination of the rows, we sort of update the set S, we shrink this set, and we're hoping that we're going to shrink it all the way down to the point where it's like more or less equal to the set we're looking for. At that point, we're going to be able to decide that f of X equals A of X holds if X is in S. Basically, membership in S will, at that point, be a pretty good proxy for whether f of X equals A of X or not. Okay, so to analyze this, you define this probability potential P. It's equal to the conditional, like the probability that f of X equals A of X conditioned on being in the set S. At the beginning, when S is everything, you have P is just epsilon. And at the end, we're hoping that P is roughly equal to 1. That's the hope of the algorithm. So the crux is we want to show that P increases each time through the main loop. Specifically, what we want is that P increases by a multiplicative factor that's slightly bigger than 1. If so, that's going to let us set sort of T to be log of 1 over epsilon, and that's going to get us the running time that we sort of gave in the claim. Okay, so let's analyze the main loop. Let's see if this works. The key quantities here are P. I'm not sure we need Q of V yet, we might, but P is sort of what I defined. P is this conditional probability of being equal to A, given that you're in the set S. Q, if we need it, I'll tell you what it is. And the main loop has sort of 3 steps, but 2, like the first is just drawing a random Z. So the 2 main steps are where you invoke the one-dimensional Goldreich-Levin theorem to recover A transpose Z. To analyze this, okay, so we do need Q. So Q is basically the probability that the linear condition holds given that you're in S. The probability that Z times f of X equals Z times A of X given that you're in S, and it's a function of Z. And the Goldreich-Levin theorem is going to work. It's going to work with probability epsilon cubed if Q of Z is at least 1/2 plus epsilon over 4, or 1/2 plus delta. Okay, remember that the sort of the hypothesis of the one-dimensional Goldreich-Levin theorem is that you need the agreement to be bigger than 1/2. Okay, so we need this Q of Z to be, we need this Q of Z to be bigger than 1/2, namely 1/2 plus epsilon over 4, in which case one-dimensional Goldreich-Levin theorem says that we recover A transpose Z with probability roughly epsilon squared. And then there's the update step. So when we update S, we're hoping that we're shrinking S by a significant amount, right? That's going to represent progress towards sort of getting closer to recovering S. And if you do the computation of this P, this sort of potential P that we defined before and after you change S, the new P is going to be equal to the old P divided by Q of Z. Okay, so in addition to needing Q of Z bigger than 1/2 plus epsilon to make progress, you also need Q of, you also need Q of Z smaller than 1 so that you make progress towards finding S. Okay, and so, we're going to basically, 0.99 is kind of going to allow us to make sufficient progress so that we get that constant multiplicative progress each step. Okay, and so basically to sort of summarize, if the Q that you picked, if the Z that you picked has this Q that's bigger than 1/2 plus epsilon and less than 0.99, you're going to make progress towards recovering that step Z, constant multiplicative progress. And this is what we're hoping for because this is going to give us that runtime.
Are you going to say the same Z? Or
No, we're going to pick a random Z each time. Each time we, hopefully we get lucky in our choice of Z. We're going to have Q of Z bigger than 1/2. We run Goldreich-Levin, hopefully we get lucky, we recover the right thing, and then we sort of update S, and hopefully we get lucky, Q of Z is less than 1, in particular less than 0.99. That's going to mean that the new P is going to be constant multiplicative bigger than the old P.
So having too good of an agreement.
Yes. Yeah, we'll say that. And actually this algorithm doesn't work basically because there are functions where you have like excellent agreement all the time with Z, and yet it doesn't work. So we'll talk about it. So yeah, it's a little counterintuitive. You need both a bound on how good Z is and also like an upper and a lower and an upper in order to get this to work. And okay, if you sort of the analysis of the full algorithm is going to follow from this. Basically, this is the key thing. You need the probability that you're greater than 1/2 plus epsilon over 4, but less than 0.99 to be not too small. If you're not too small, then you're going to make sufficient progress each time. You're going to be good. Okay, so the question is, what's up with this sort of probability here? Is it true that this is going to like hold for every f, or are there counterexample f's where this does not hold? And let's look at sort of what's going on. Okay, so again, this is the important condition. It's important enough to give it a name. Let's call it the GLPC, the Goldreich-Levin progress condition. If the Goldreich-Levin progress condition holds, then the sort of one step of that process is going to make progress towards our whole objective. And the claim that we just stated is if the Goldreich-Levin progress condition holds, then progress occurs in the main loop with probability like epsilon cubed or fourth or something like that. So the question is, does it hold? And let's look at this point, let's look at two different examples. One is going to be one where it works and one where it does not work. And this is the one that we've already seen. It's f of x is just a random bit, and then it's just fully a of x. This is the one where it doesn't work. Remember, I said at the beginning, this is kind of the like most annoying counterexample. Let's look at one where it does work. And this was kind of a version of the alternating type of example. So you have two matrices, A and A prime, and you have some partition of the space. And you know, if you're in partition number 1, then a of x equal, so then f of x equals a of x. If you're in partition number 2, f of x equals a prime of x. And let's, you know, partitions are of equal size, let's say. The key quantities are here. Remember, sort of P is this potential. It's probability of agreement with a condition on being an S. And Q is the probability that the one linear condition, like the linear condition defined by Z holds condition on being an S. Okay, in both examples, P is roughly a half. We're going to assume that basically A and A prime don't have good agreement amongst each other. So you have very small chance of being like of agreeing with both, basically. And here, this is going to be just agreement on 1/2. It's just action equals, right? Because it's just whether you get the first bit correctly or not. And let's go through sort of the analysis of example 2. This is the one where our greedy algorithm does work. So, okay, P equals 1/2. Q of Z. What's Q of Z? Well, Q of Z is going to be the probability that Z times f of x equals Z times a of x, given that x is an S, but S is everything right now. This is the first execution of the loop. Okay, so what's that going to be? Basically, it's going to be like Z times f of x equals Z times a of x is going to hold with probability 1 when you're in the sort of good partition, and it's going to hold with probability 1/2 when you're in the bad partition. 1/2 over Z, right? Half of the Z's are going to be such that it holds. Half of them are going to be that. No, I'm sorry. It holds for every Z because half of the X's are going to be where even if f of x is not equal to a of x, you know, half of the Z's are going to be such that it sort of, the linear combination holds, even though you have two different things, right? So the probability is 3/4. Sorry, I just like butchered that computation, but basically half the time you're in the good partition, half the time you're in the bad partition where the probability is 1/2. Okay, so that's 3/4. When you update, sort of the process of the procedure of updating S and then defining a new S, the new P, remember, is equal to the old P divided by Q of Z. So basically 1/2 divided by 3/4, that's 2/3. So you're going to increase the new P. Okay, and that makes sense thinking about it, because given that you agree with the linear combination that you found, the chance that you're equal to A of X is higher, right? Assuming that you recovered one linear combination of the rows of A, you're going to have agreement with A. Every time you have agreement with A, you're going to satisfy that linear combination. And only half the time when you agree with A prime, you're going to have that linear combination. So the probability that you agree, given that you're an S, has gone up. Okay, if you do this one more time, now S is different. S is going to be the, the 3/4 of the space where the linear combination holds. And you can compute in that space, okay, Q of Z now is 5/6. And then when you do it again, you get 4/5. And the point is P is getting closer and closer to 1. It's not just going to go, yeah, this will be kind of an exponential thing. It will. Yeah, it's, I think it's like 2 to the. Yeah. This looks misleading. Yeah, it's going to go exponentially. Yeah, exactly. Right. Exactly. And this is the good case. This is when you actually make like even more progress. If everything works like this, you'd get a constant, it would be, you'd only need a constant number of steps. Kind of, maybe that's not quite true. But anyway, okay, this is sort of the example where things work as we hope. This is where our greedy algorithm does actually work. Okay, in this example, so again, this is the example where the first bit's random, everything else is equal to A of X. So P is 1/2 because it's just dependent on the first bit, but what's Q of Z? So Q of Z, if you look at it, if Z1 is 0, then you're killing the first bit of the output. So it's just going to agree perfectly. If Z of 1 equals 1, then your inner product Z times F of X is just a random bit. So the chance that agrees with Z times A of X is just 1/2. Okay, and so this is an instance where that Goldreich-Levin progress condition does not hold. Q of Z is either equal to 1/2, in which case you make no progress because Goldreich-Levin doesn't work, or it's greater than 1/2, but it's so good that you don't actually like shrink S at all. And that makes sense, right? Because if you like, given that your X satisfies a linear combination where Z1 is 0, you're killing the first row. Like just because like X that satisfies that condition, it gives you no information about whether the first bit is correct or not. So you shouldn't expect to make any progress in this case. Does this make sense? Okay, so we have this sort of mathematical criteria that lets us make progress, that Goldreich-Levin progress condition that says as long as Q of Z is above 1/2, but below 1, we're going to make progress. This is an example where Q of Z is either always equal to 1/2 or equal to 1. So we're never in that sort of nice middle ground that'll let us make progress. So this is basically an example function that does not work, given that mathematical criteria that we put. Intuitively, why should this not make sense? Agreeing with a linear combination where Z1 equals 0, it doesn't give you any help at whether F of X equals A of X or not. Because the first bit is random, but there's no information about the first bit in that linear condition. So your chance of satisfying of being equal to A of X is still just 1/2. It's whether or not the first bit is correct or not. And the linear combination you have gives you no extra help as to whether that's satisfied. Okay, so yeah, your P is still going to be this. So the problem is that Goldreich-Levin progress condition does not necessarily hold. Algorithm is not going to make progress in this case. Now, so we need something a little smarter than this basic greedy algorithm. And the main contribution, I would say, of this work is kind of characterizing the situations where you're in kind of this type of situation. And it turns out that you can kind of understand whether or not you're in, somehow this is like the only thing you can do to prevent making progress through this. You can basically be adding a random vector from some small subspace. And you can kind of, using other methods, figure out what's the you can figure out what's the subspace, and then you can kind of like make progress in a different way to handle that. So I'm going to explain that, but that's kind of the main idea. It's like sort of characterizing all of the places where that nice sort of type of progress that we had in mind doesn't work, categorizing all of them, and then dealing with them. Okay, so here's the main claim that allows you to make progress when Goldreich-Levin progress condition does not hold. It says that if the Goldreich-Levin progress condition does not hold, then there exists some non-zero vector W such that the chance that you're equal to A of X plus something that's in the span of W is greater than, by a constant factor, the probability that you're just equal to A of X. So basically, all of the functions that have that type of like failure for the basic greedy algorithm are doing something along the lines of example 1. Namely, they're equal to A of X fully, except for they're outputting some random vector from some small subspace. Okay, and so you can get that nice multiplicative progress if you just sort of like relax what you mean by A of X equaling A of X, by F of X equaling A of X. We no longer want strict equality, F of X equals A of X. We're now okay with like F of X being, you know, in A of X plus something in a small subspace. Right. And so algorithmically how this fits in is a little bit unclear still, but I'll explain. But basically that's the idea. And if you look at this counterexample, this is the same counterexample. I think I switched the, sorry, I switched the one that used to be on the top, but it's still outputting the first random bit followed by A of X. The probability that F of X equals A of X is 1/2, but the probability that F of X is in A of x plus the span of like the first unit vector is 1. It's always either equal to A of x or it's A of x plus the first unit vector. And so in this case, by relaxing what we mean by A of x, by f of x equals A of x, we're going to be able to make a lot of progress. Okay, the proof of this claim is Fourier analysis. We're basically going to find a plane by looking at the heavy Fourier coefficients of this function q of z. And I'll leave the proof written here. It's pretty fair. I can go through it if we have time, but we're over time over. It's up to. Yeah, this is like the end, basically. Okay, so finding heavy Fourier coefficients, again, is sort of something that the original Goldreich-Levin lets you do. The problem is that this q is not an efficient function. We don't know a, and so we can't actually compute this. Sorry, we can't actually compute this function q. No, because we don't know a. We don't. Yeah. But you sort of like, you can compute the Fourier coefficients of this function q of z, and it turns out that q hat of w is exactly equal to the thing that we want. It's just probably that f of x is in ax plus the span of w. And sort of the key sort of point is that if the Goldreich-Levin progress condition doesn't hold, then this function q has high variance. It's like, it's always either less than, like, very close to 1/2 or close to 1. So it has high variance. So that means it has basically a heavy Fourier coefficient, because there's this like, you can write the variance as a sum of these Fourier coefficients. And, you know, it's a little more complicated, but this is more or less the same thing. So essentially, if the Goldreich-Levin progress condition does not hold, function has high variance, therefore there's a heavy Fourier coefficient. Sorry, and it turns out that the Fourier coefficients are exactly sort of the probability that we're looking for up here.
So you find organized, so maybe still.
Right. And again, you can do the thing where you just sort of find one at random, and you're not actually finding it. This is kind of maybe a confusing piece. It's sort of the only like the full algorithm is that greedy algorithm. It's just as far as the analysis goes, sometimes the greedy algorithm doesn't let you make progress, in which case you have this like existential step where you just increase what you mean by equality holding, and you can kind of make progress that way. And then, so basically the algorithm and the analysis kind of looks like this. Same thing. S is initialized to be the entire space. This blue set is what we're looking for. And this blue set now is the set of all x such that f of x is in ax plus w, where w is initialized to 0. So you keep track of now two things, the set S and this vector space W that's like extending what you mean by equals. And okay, let's say you like the Goldreich-Levin progress condition holds, great. Then that greedy algorithm is going to shrink S just like we saw before. Let's say the Goldreich-Levin progress condition holds, great, shrink S just like before. Let's say the Goldreich-Levin progress condition does not hold, then you know that by increasing what you mean by equals, you're going to be able to make the blue set bigger. Likewise, you know, if it does not hold, you make the blue set bigger. If it does hold, you increase. And importantly, you're only ever running, the only algorithmic thing that's happening is you're running the greedy algorithm. It's just you're sort of pausing in between sessions to say, does the Goldreich-Levin progress condition hold? If not, let's sort of re-understand what we mean by being equal to, and let's run the same greedy algorithm, but with a different notion of, basically, let's update the potential that we're using to keep track of how close we are. And by the end,
So you keep
in the analysis, the algorithm does not. The algorithm is agnostic to the W. You just run greedy algorithm. In the analysis, you keep track of the W. And you can basically say either you're going to make progress using the greedy algorithm, or you're in a situation where you're not going to make progress, in which case, existentially, we just increase the potential. And by the end of it, you'll be guaranteed that, you know, you're not going to have f of x equals a of x anymore, but you'll have f of x being in a of x plus w with probably very close to 1. And this is just as good. Like you can, I mean, I'm not going to show it, but sort of recovering a and w from this condition is much easier. Once you're close to 1, you can kind of use some union bound stuff, and it goes much faster. So, right, exactly. So that's why there's always this like epsilon to the 1 over epsilon, exponential in log of 1 over epsilon. No, it won't be 1 over epsilon. Sorry, I apologize. I didn't hear what you said. Did you say log of? No, the dimension of W increases by 1 every time you run the loop. So it's going to be at most log of 1 over epsilon. Yeah. And that's it. Sorry.
Wouldn't there be more than one W in the program?
Yeah, somehow like you're kind of
the one and either half or 1.
Yeah.
So there could be
yeah. Yeah.
So in this case, you don't only recover A, you can actually also say that like all A primes that look like A differ by this like.
Exactly.
Like a low rank matrix, W is like the image.
Exactly. Yeah. So the W is basically we're saying we can recover A and like the whole family that's sort of exponential size because you're just outputting a random something from this low rank matrix. Yeah. So you get sort of the statement that yeah, basically you get a pretty like full description of the family of a group that explains A. Yeah. So that's it. Are there questions? I'm happy to answer questions if